This scene deals with the subject many fathers find so difficult.
Welcome to podcast V0.1, where we break down the latest research and tools for curious engineers. You've probably heard Kubernetes called the Linux kernel of the cloud. It's a powerful analogy. Kubernetes provides that core orchestration layer, managing containers and services across a fleet of machines. But just like with Linux, very few people run the raw kernel directly on their servers. Instead, you run a distribution, a Debian, a Red Hat, an Ubuntu, a SUSE, something that packages the kernel with essential utilities, default configurations, and a specific philosophy about how things should work. Well, what happens when you want to run Kubernetes not in a cloud provider's managed environment, but on your own hardware, on-premise? Suddenly, you're faced with the same challenge. Kubernetes itself, the upstream project, is incredibly flexible and pluggable. That's its strength, allowing it to adapt to countless environments and workloads. But that flexibility comes at a cost, especially for on-prem deployments. It forces system administrators, maybe even you or your team, to make a whole lot of choices up front. Think about it. You need networking. How will pods talk to each other? How will services be exposed? Kubernetes doesn't mandate a specific solution. It offers the Container Network Interface, or CNI, and essentially says, pick one. The paper mentions Calico seems popular in their community, but there are others like Flannel, OVN Kubernetes, and more. Same for storage. Need persistent volumes for your databases or stateful applications? Kubernetes provides the Container Storage Interface, or CSI, defining how storage systems integrate. But you need to actually choose and integrate a storage provider, perhaps the popular Ceph distributed storage system via Rook, maybe something simpler like a local path provisioner or a commercial solution. Then there's monitoring, logging, security configurations, routing traffic via ingress controllers, managing TLS certificates. The list keeps growing. Simply installing the core Kubernetes components, the API server, the etcd distributed database, controller manager, scheduler, kubelet, doesn't give you a production-ready cluster. It gives you the engine, but you still need to build the rest of the car around it. This complexity can be daunting. That's where the idea of Kubernetes distributions comes in, and it's the central theme of a recent paper titled Kubernetes Deployment Options for On-Prem Clusters by Bryant, Gardner, Hugh, Jordan, and Taylor, published on RX4. The paper essentially explores the Debians, Red Hats, and SUSEs of the on-prem Kubernetes world. It analyzes and compares different approaches that bundle Kubernetes with specific tooling, default choices, and opinions to make deploying and managing a cluster on your own infrastructure significantly easier. The goal is to help site administrators, or platform engineers like many of us, choose the right distribution that fits their specific needs, expertise, and constraints. The paper focuses on three popular families of these distributions. First, there's the minimalist approach, represented by Kubeadm and often deployed using a tool called Kubespray. Think of Kubeadm as the tool provided by the upstream Kubernetes project itself. It's designed to bootstrap a minimum viable Kubernetes cluster. It gets the control plane up etcd, API server, etc., and lets you join worker nodes. But that's about it. As the paper notes, it's intentionally unopinionated, meant as a building block for higher-level tools. Kubespray is one such higher-level tool. It uses Ansible, a popular configuration management tool many engineers are familiar with, to automate the deployment of a Kubeadm-based cluster. Kubespray provides sensible defaults and can deploy across various Linux distributions, offering high availability options. It gives you a lot of flexibility to choose your own components, your CNI, your storage, your ingress controller. But the flip side is, you have to make those choices and integrate those extra components yourself, as they aren't included. The paper points out a potential drawback. Kubespray uses a push-based model via SSH. This works well for initial setup and upgrades if you have SSH access from a central provisioning node, but might be less suitable for environments where nodes need to be dynamically added or removed without relying on outbound SSH connections from that central point. Second, we have the highly integrated, highly opinionated end of the spectrum, OpenShift, and its upstream open source version OKD from Red Hat. The paper groups them together, referring to them as OKD for simplicity in its analysis. If Kubeadm/Kubespray is like building from a minimal base Linux install, OKD is more like an enterprise Linux distribution, with a large suite of integrated tools and strong opinions. Red Hat positions OpenShift OKD as an enterprise platform with built-in features for multi-tenancy, CI/CD pipelines, a container registry, monitoring and log aggregation stacks, typically based on Prometheus and Grafana, and even virtualization capabilities. A key differentiator highlighted in the paper is OKD's deep integration with Fedora CoreOS or Red Hat Enterprise Linux CoreOS in the commercial version. CoreOS is a container-focused, immutable operating system. OKD leverages CoreOS and a tool called Ignition for provisioning. Ignition uses declarative configuration files to set up everything on the node: disks, file systems, services. This enables an immutable infrastructure approach where OS updates are atomic. The server essentially boots into a completely new OS image. Nodes are treated as ephemeral objects, much like containers. The paper notes OKD can even manage nodes down to the baseboard management controller using the Redfish API. This sounds powerful for consistency and scalability, but the paper cautions that this tight integration and assumption of control over the entire node lifecycle might be challenging to integrate with existing site provisioning infrastructure that doesn't follow this model. OKD also mandates high availability from the start. The paper notes it requires a minimum of 4 nodes, a dedicated provisioner node, plus 3 control plane nodes, just to get bootstrapped, unlike other distributions that might allow a single control plane node. Third, the paper looks at Rancher, developed by SUSE. Rancher is positioned somewhere between the minimalism of Kubeadm and the all-inclusiveness of OKD. It aims to provide a balance, offering many features like a web dashboard, centralized cluster management, and options for security-conscious environments, but perhaps with more flexibility in underlying OS choices compared to OKD's tight core OS integration. Rancher actually offers 2 distinct Kubernetes distributions under its umbrella, K3s and RKE2. K3s is fascinating. It's designed as a lightweight, fully compliant Kubernetes distribution optimized for edge computing, IoT, CI/CD, or resource-constrained environments. It achieves this by removing optional in-tree cloud provider and storage plugins to shrink the binary size. It bundles essentials like a networking plugin, Flannel by default according to the paper, DNS, Core DNS, and an ingress controller, Trafic. One really unique feature mentioned is that K3s allows you to swap out the standard distributed key value store, etcd, for a traditional SQL database like SQLite, Postgres, or MariaDB. This could significantly lower the operational complexity for teams more familiar with SQL than etcd, especially for single node or small clusters. However, the paper notes that the default SQLite backend isn't suitable for highly available control plane setups. RKE2, also known as Rancher Government, is Rancher's other distribution. This one is focused squarely on security and compliance, particularly targeting U.S. federal government standards, like FIPS, Federal Information Processing Standard, and being DISA STIG certified. Compared to K3s, RKE2 tracks upstream Kubernetes, releases more closely, uses the standard etcd data store, defaults to a high availability control plane configuration, requiring an odd number of control plane nodes, and generally bundles components with a stronger security posture. According to the paper's comparison table, RKE2 supports several CNI plugins. Notably, RKE2 encrypts Kubernetes secrets at rest by default using AES-CBC encryption, which is a significant security enhancement compared to standard Kubernetes, where secrets are just base 64 encoded in etcd unless you explicitly configure encryption at rest. So the paper lays out these 3 distinct philosophies: the flexible but requires assembly Kubeadm/Kubespray, the tightly integrated, feature-rich but potentially restrictive OKD, and the versatile Rancher offering both a lightweight edge option, K3s, and a security-focused enterprise option, RKE2. How do they compare in practice? The paper includes helpful comparison tables. For provisioning, Kubespray uses Ansible over SSH. OKD has multiple installers: web-assisted, automated via command line, agent-based for restricted networks, and manual, but relies heavily on that core OS ignition model. Rancher, K3SRKE2, typically uses a command line utility or agent-based registration. Minimum node counts differ significantly, impacting initial cost and complexity. Recall OKD's requirement for a 4-node minimum for its default HA bootstrap, versus Kubespray needing 2 nodes, bootstrap plus control plane, and Rancher potentially starting with just 1 node. Operating system support varies too. Kubespray supports several common Linux distros. OKD is tightly bound to Fedora Core OS, while Rancher also supports several distributions according to the paper. Perhaps the most critical comparison for engineers day-to-day is the handling of essential add-ons, which the paper details in its table 2. Persistent storage, not included with Kubespray. You need to set up something like Rook with Ceph, Rancher's Longhorn, or another CSI driver yourself. OKD offers OpenShift Data Foundation, based on Rook and Nuba, while Rancher promotes its own solution, Longhorn. A load balancer for exposing services on bare metal? Again, not included with Kubespray. You'll likely need to install Metal LB or Pure LB. OKD integrates Metal LB according to its documentation cited in the paper, while Rancher offers options. Ingress controller? Kubespray leaves it to you. Genix and Treffic are popular choices. OKD uses an hproxy-based controller. Rancher typically defaults to Index according to the paper. This pattern continues for HTTPS certificate management, tools like Cert Manager, external DNS integration, tools like external DNS, GitOps tooling, like FluxCD or Argo CD, and web interfaces. Kubespray provides none out of the box, maximizing flexibility, but requiring manual integration. OKD and Rancher tend to include or offer tightly integrated solutions for most of these. For example, both OKD and Rancher bundle Prometheus and Grafana for monitoring and alerting by default. Both provide custom web dashboards. OKD offers OpenShift GitOps based on Argo CD as an optional integration, while Rancher has its own GitOps tool called Fleet. OKD also offers optional operators for integrating Cert Manager and external DNS. This clearly illustrates the fundamental trade-off. The minimalist distributions give you maximum control and flexibility, but demand more effort and expertise to assemble a complete, production-ready system. The more opinionated, integrated distributions offer a faster path to a feature-rich cluster with potentially lower initial operational burden, but they come with their own set of opinions, preferred tools, and potentially a greater degree of vendor or ecosystem lock-in. So how well does that initial Linux distribution analogy hold up? Pretty well, actually. Just like choosing between Debian, stable, community-driven, huge package selection, Fedora, more cutting-edge, upstream for Red Hat, and Ubuntu, popular, user-friendly, choosing a Kubernetes distribution involves similar considerations about stability, features, support, community, and operational philosophy. What does this mean for you, the software engineer, or your platform team? First, consider the potential for lock-in. Using Kubeadm and Kubespray keeps you closest to upstream Kubernetes. You're integrating standard open-source components. While you depend on those components, you're less tied to a single vendor's ecosystem. Choosing OpenShift means buying into the Red Hat ecosystem, its specific tooling like OpenShift Data Foundation, its core OS dependency, and its release cadence. Similarly, Rancher brings you into the SUSE ecosystem with tools like Longhorn and Fleet. This isn't necessarily bad. These ecosystems offer significant value and support, but it's a strategic choice with long-term implications for compatibility, cost, and required skill sets. Second, think about the learning curve and operational burden. For a team new to on-prem Kubernetes, an opinionated distribution like OKD or Rancher could significantly lower the barrier to entry. They handle many complex integrations for you, providing a working cluster with monitoring, storage, and ingress relatively quickly. However, managing these integrated systems long-term requires understanding their specific way of doing things. Upgrades might be more streamlined within the distribution's framework, But troubleshooting might require digging into distribution-specific components. Managing a Kubespray cluster might require more initial effort to set up all the pieces, but you have direct control over each component, potentially making troubleshooting or swapping components easier later, assuming your team has the expertise. The operational difference between managing SSH access for Kubespray versus dealing with OKD's immutable core OS updates via Ignition is quite profound. Third, while this paper comes from the high-energy physics computing community, the challenges and solutions discussed are broadly applicable. Whether you're running scientific computing workloads, enterprise applications, or modern microservices, the fundamental need for reliable networking, storage, monitoring, and deployment automation on Kubernetes remains the same. The specific performance needs might differ, but the architectural choices presented by these distributions are relevant across domains. The paper also highlights some interesting trends. OKD's embrace of immutable infrastructure with Core OS and Ignition is a significant one. Is this the future for managing server fleets at scale, treating servers like cattle rather than pets, even on-prem? Or is it too restrictive for organizations with established provisioning tools and diverse hardware? The existence of K3s also points to the growing need for Kubernetes, not just in massive data centers, but also in smaller, edge, or resource-constrained scenarios. The ability to use a SQL backend instead of etcd is a pragmatic engineering choice that could make Kubernetes accessible to new use cases and teams. Finally, an interesting side note mentioned in the acknowledgments. The authors explicitly state they utilized ChatGPT during the drafting process for enhancing text clarity, finding literature sources, which they then verified against their own experience, and developing narratives about the cloud-native landscape. It's a fascinating glimpse into how AI tools are starting to be integrated into scientific research and writing, with appropriate transparency. So what's the main takeaway? Deploying Kubernetes on-premise involves navigating a complex landscape of choices. There's no single best way. The concept of Kubernetes distributions helps frame the decision. You need to weigh the flexibility and control of minimalist approaches like Kubeadm/Kubespray against the integrated convenience and potentially faster ramp-up of opinionated distributions like OpenShift/OKD or Rancher. The right choice depends heavily on your team's expertise, your organization's existing infrastructure and tooling, your tolerance for vendor ecosystems, and the specific requirements of your workloads, particularly around things like security, compliance, and high availability. Understanding the philosophies and trade-offs presented by these different distributions is crucial for making an informed decision. That's all for this episode of Podcast V0.1, and remember to never stop learning.